Welcome. I asked for a 2-hour block, and I got a 45-minute block, and now I have like a 35-minute block. So let's go. I'm John Medina. I've been breaking things, hacking things since I was 12. Many apologies to the Hemet Public Library in Southern California. Their poor networks took a beating from young me. And so it's especially special for me to be up here speaking to you all because you all, growing up, you all were rock stars to me. Like this is the pinnacle of where I wanted to be and never thought I would be. So thank you very much for having me. I appreciate it. I love this stuff. I'm currently a consulting network security architect is kind of the box that I would put myself in. I work for an awesome company called Protiviti, and I get to go around the country to various companies and break them, make them, worry about themselves a little bit, and then go in and help them and help fix some of the problems that we find and some of the issues that we see there. I absolutely love what I do. A little bit about what we're talking about today and why I think this talk is important. So, software-defined networking is no longer a brand new technology. I'm not coming here to tell you about this new bleeding-edge technology that is just being discovered. As some of you have seen, software-defined networking has been around a while. It's now in use in many large companies. However, there's very little presence of software-defined networking talks and security-related software-defined networking talks specifically among these communities. I'm the second person ever to talk on software-defined networking at DEF CON. And last year, another team of researchers were some of the first ones to talk about it at Black Hat. SDN has been around for years, and why is this not getting more visibility? And so I'm not going to assume any knowledge here. We're going to start at the beginning and show you exactly what a software-defined network looks like. I'm breaking all rules of Tech Talks and not doing only one live demo, but 2 live demos. So we're not off to a good start here, but we'll see how it goes. Moving on. Why software-defined networks? Why do we care? Why do we need them? Well, as many of you know, networks have been around a very long time, and not much has changed in a very long time. The TCP/IP stack, you can go buy those awesome 2-volume books that many of you are probably familiar with on the TCP/IP stack. Read those today. They were written how many ever years ago, and they are still just as relevant today because not much has changed. However, the architecture that we're using over the top of these networks has changed drastically with cloud migrations and new types of networking, virtualization. Lots has changed, and networks in many cases have not kept up. From a security perspective, why can Alice and Bob, for example, working on the same floor of a company's computers talk to each other? There's no reason for that. At no point should 2 people in 2 separate cubicles, computers, really need to ever talk to each other. They have their certain resources they go to, and they should be limited to those. However, networks are designed to make things communicate. And so that's just what they do, and they do it well. So in that way, they work too well. Things are talking that shouldn't be. And along the same lines, firewall rule lists are starting to get out of control. In addition, they don't work well enough. Provisioning network resources is expensive, time-consuming, and it's very difficult. How do you know when you're deploying a new system, a new server, how much bandwidth to allot that? You are stuck with a fixed amount of bandwidth, giving that to that particular system. Infrastructure deployment is very expensive. For those of you working on the infrastructure side, I don't know how many of you have deployed a Nexus switch lately. They get a little pricey. So prices are going up, devices are getting more complicated, and how does this all translate as we move to the cloud? Well, I'm hopefully going to demonstrate a little bit of the cloud side here, as my demos are all taking place in the cloud. So, a little bit about software-defined networking. So, the core behind software-defined networking, the logic there is moving the control plane outside and the data plane outside of the devices. So our network devices now become a lot dumber. And the logic, the brains behind it is now the software-defined networking controller that sits at the top of the network. So the controller is what makes the decisions for the switches. And if the switches don't know how to handle something, they ask the controller. And we'll go into a little more detail on that a little bit later. I do want to make clear this is not network functions virtualization. So you go into AWS, you can download an AMI for Brocade switch, Brocade routers, Juniper firewalls. That is network functions virtualization. That's actually taking the network hardware and virtualizing it. That's not what this is. This is a completely different, and those can integrate with software-defined networking, but software-defined networking is dramatically different from that, and I'll show you what I mean by that here in just a moment. How many folks in the audience have interacted with software-defined networking or know that it's in place in your companies? Look around. There's a solid amount of hands up right now, and so I'm really glad you all are here, and I look forward to interacting with you after the talk or during the questions here. So just a quick overview of what software-defined networking is and how it works. First of all, what's out there? So there are closed source and open source versions. Of course, Cisco has a closed source one. And I say that as a Cisco network engineer in my past. I enjoy Cisco stuff, but Cisco and VMware have done their own kind of closed source proprietary versions of it. They work quite well. The open source companies have used open source open flow controllers that use all open source protocols, and their APIs allow you to integrate things with them. Like I said before, not a new technology. Go on to LinkedIn and do a search for software-defined networking, and you'll see how many companies out there are using it. It's a lot. Google, Amazon, Facebook, NSA, and most telcos, most of the 5G systems that are getting rolled out are all being rolled out within a software-defined networking architecture. Closed source or open source, all SDN architecture is going to look very, very similar to this. So it's divided into three real segments. The top segment is the application layer, and that's where your business applications can interact with the SDN controller to provision network resources or monitor network traffic in any way they want. And that's done through API calls to the control layer, which actually holds the SDN controller. And I'll demonstrate the capabilities of that here with a tool that I worked with some folks on creating for this purpose. After the control layer is the infrastructure layer. That in between there is the OpenFlow protocol, where the OpenFlow controller or this SDN controller communicates with the switches. What's cool about this is when deployed in a recommended scenario, the control channel between the controller and the switches is actually on a completely separate, is physically separated from the data channel where the switches actually go to your hosts at the bottom. And so it's with that kind of setup, it's almost impossible without manipulating the firmware of the switches to jump into the control channel. And unfortunately, because I'm short on time today, I'm not able to go into a whole lot of the red teaming side of things with the SDN controller, but there's some really cool things about compromising SDN controllers and taking over control channels. I spoke a little bit on that at ShmooCon last year. So core concepts. First of all, I apologize for the graphic. This slide was really bare without it, and so I just Google image search, and that was the first thing that came up when I typed in flow, and I was drunk, and it ended up in there. So core concepts of SDN. The controller sends flows which look a lot like ACLs to switches. The switches then make decisions based on those flows and forward traffic to its various destination based on that. And we'll talk more flows in just a second. If a switch doesn't have a flow that matches a certain type of packet, it asks the controller. And then the controller can either tell it, hey, drop it, here's a new instruction, start sending those flows this way, or it can send any number of instructions to the switch on how to treat that flow. And once again, we'll talk more about that in a sec. Or you can finally just have a drop. So it's almost like a firewall rule set. So at the very bottom is your drop set, and if nothing matches any of the flows already in the switches, just kill it. It doesn't belong there. This is what a flow looks like inside a switch. So first is the rule, which is the match information. And that tells the switch what to look for in the packet. Now, natively, it supports pretty much layer 1 through layer 4. So it can match anything within the packet, all the way from what port it came into on the switch, to the MAC address, to the VLAN, to the IP address, anyway, all the way up to port and protocol. Once you start integrating different programs, different business programs, as we discussed through the APIs, it can now look all the way up through layer 7. And you can actually find program data within the packets and match that with inside an SDN controller. So that first blue section there, I think that's blue, I'm colorblind, is the match area. The next part is the action. So what action is that switch going to perform on that packet once it matches that criteria? Lots of possible opportunities, and many of them will cause your ears to perk up a little bit, as we'll demonstrate later. One is it can just forward packets to ports. So it says, hey, if I see things inside this port, forward it out that port. Or if I see it coming in from this IP address, forward it to that IP address. You can make it have very traditional switching behavior if you wish. Some other cool things, though, is you can overwrite data inside the packet. So you can have your hosts believing they're on one subnet, when in reality, as soon as their traffic hits the switch, all their subnet, all their IP addressing information is rewritten and sent someplace else. So you can now spoof hosts anywhere in the network. You can move hosts wherever you want in the network. And you can do this to either secure or actually attack a network, as we'll show here shortly. And many other things. So the normal processing pipeline is hey, switch, behave like a switch. Just do your switching thing. If something weird comes up, send it to the controller. And then obviously dropping packets are another option there. So I'm going to fire up an SDN here, and we can actually look at it. Let me get set up here. All right. My VPN disconnected, so I just need a minute for that to stand up. There we go. So here is the OpenFlow controller. I chose to use the Floodlight controller today. As I said before, there are many other vendors. This one is an open source product of the Big Switch company. It's very stable. It's in use in production, and Big Switch has all kinds of cool things you can add into it if you so choose. Let me just give you a short walkthrough of this. So here on the dashboard, you can have multiple controllers. So you can actually have kind of a split brain type logic for your network, if you choose, where controllers can communicate to each other about different portions of your network. And that can provide some very high level type segmentation as well as high availability. This will show you switches, hosts as soon as we set it up. But a couple other things that I want to point out that we're not going to get into today is you can perform firewalling at the controller level. So before the controller even performs logic internally on the switches, you can immediately define, hey controller, these two things should never be allowed to talk, or this network should never be allowed to talk to this network. And that's processed prior to any other logic done in the controller. And it can be done in more of a proactive way. So you can actually be sending dynamic firewall rules to the controller as it sees malicious traffic. Let me stand up our Mininet here. So Mininet is a great program. How many of you have heard of Mininet or worked with Mininet? Okay, handful of you. I highly recommend it to everyone, even not for SDN. It's a great tool. So I don't want to type all this out, so I'm just going to copy and paste it here. Oops. So what Mininet does is it simulates a network of switches of any real type you want. And in this case, it can also simulate SDN switches. So what I've done here is created, actually, let me do a little cooler network. This one's not very fun. Let's see. Yeah, let's do this one. So you can build custom topologies. They're really, the possibilities are endless. And it stands up hosts underneath those switches. So once you stand up your switches, it will also connect hosts to them. And you can interact with those hosts in any way you choose, as you'll see here. So this is going to take a minute for it to discover everything. So as you can see now, we have 9 switches connected to the SDN and 131 hosts, all of which are run as mini bash instances on your host mininet machines. So you can go in on them, you can nmap from them, you can run anything you can access from bash, you can do on those hosts, which is super cool. So this is a network we just stood up. So there we are. And right now, as you can see, whoo, squid. As you can see, there's a core switch with basically what the topology I like to use kind of simulates more of a data center environment. So this, you'd see it as almost as a core switch. And then each one of the other switches around there are top of the rack switches with hosts below them, is how I like to visualize it. And we'll go into that a little bit later when I show you some of the security functions of this. But once the SDN controller, so let me show you a few of the flows inside the switches here. So right now, the switches don't know much about their life. So let's go into switch number 2 here. So here's the flow table. It has one single lonely flow in there, and that means output to controller. So the switch has no instructions right now. It doesn't know what it's doing. All it knows is, hey, if I see a packet, immediately send it to the controller because I have no idea what I'm doing. These 234 packets are LLDP packets, which is a core functionality of OpenFlow, which has some security implications in and of itself, as you can imagine. But that's what the controller uses. The controller sends LLDP broadcasts, and that's how it actually knows that these hosts are connected and that these switches are connected, through LLDP. But as you know, it doesn't know any of the IP addresses of these yet because it's only used LLDP to discover them. So let's teach these switches some things. So I'm just going to do ping all. And so it has every host ping every other host. And as that's going, let's go back to our switches. And we can now see that it's learning. So the controller is now sending flows to these switches and telling it where to redirect these packets. So you can see this packet, they're given their priority. If we go into the API, you can actually see what the match conditions were. This particular one is only matching on Ethernet MAC address. So matching and instructions. So hey, if you see packets from here, send it out there, send it out there. And as you can see, there's multiple pages, 586 entries at the moment. And that's just one switch. So that's one of the leaf switches. The core switch will probably have some fewer ones because it's just managing all 4 or 5 of those switches. So as you can see, that's what the flow table looks like. And within the floodlight controller, you can actually add static flows. And so here's what we talked about. Which switch do you want to put it on? Give it a unique name. You can give it priority. So one of the other really neat things about the flow tables is you can create flow tables within flow tables, like this flow tableception thing. And that allows you to actually have logic behind these flows. So for example, you can say, hey, I want this to be my user group, and I want all their traffic to be treated the same. I know all my users go to our 3 databases, they go to the internet, and they go to this file share somewhere. And you can have that logic programmed in as a single flow. And so when it goes through the switches, it identifies a secondary flow table and says, oh, this is a user, this IP address or this host is part of the user group. Let me toss them over to this flow table and use that logic in there. So you can actually nest and create almost like if-then statements within the flow tables. You can have active, you can change the rules whether they're active or not, so you can turn them on and off. You can also have rules that are set to timeout, which is awesome. For example, if you're doing large-scale patching or data migration operations, you can have flows that will redirect traffic at night over different channels. So one of the cool things about SDN is loops. You're allowed to have loops in an SDN. Many of you network folks know that loops are a horrible nightmare that Spanning Tree thankfully came along and saved us from most of the time. And with SDN does not care. You can have multiple links going to the same switch and it will load balance across them if you so choose. It won't loop across them, or you can have dedicated physical links for specific types of traffic. So the possibilities are really endless. Connect all your switches in a full mesh, nobody cares. Very cool, because you don't need Spanning Tree. So once again, these timeouts, you can time out the flows and have traffic redirect at certain times of day or direct based on load. So you can now load balance traffic dynamically because the SDN controller knows how much traffic is going across. That's that third part that I'm getting into here. So That third aspect here is the stats. That stats tracks the bandwidth, packet in, byte counters, how many times that flow was hit, all those sorts of things, and sends all that information to the controller, which then aggregates it and can show your high bandwidth links, all the any security issues, that sort of thing can be tracked through there. And that's how you can dynamically load balance your traffic around your switches. So let me go back here, close this out. Any questions about this first part first before I close things down here? Yes, sir.
How is routing figured into this? Looking at traditional EIGRP, something like that.
Excellent question. So within a pure SDN network, good call. So the question was, where does routing fit in? How do you do routing? He mentioned routing protocols, EIGRP, BGP, that sort of thing. Within an SDN, a pure SDN, IP addressing as we know it today is obsolete. You don't need it really at all. It's a reference that helps us in many ways to identify switches because it's what we're used to, but you actually don't need it. However, where you do need it is when you're interacting with other networks. And so the controller has plugins for routing protocols and has IP or BGP logic, it has EIGRP logic, and actually the Floodlight controller has plugins that do that, and you just have to enable them, and it does it natively. And so as soon as a BGP packet comes in, the controller can actually handle it, respond, and keep a BGP connection alive, for example, through an SDN. And so the destination network or your service provider doesn't know anything about it. Within cloud environments, it's very, very similar. So, for example, many folks here probably work on OpenStack, that sort of thing. OpenFlow works natively with OpenStack with plugins and can actually manage your traffic much like the VMware NSX does on the back end, and manage your traffic for whatever you stand up in OpenStack. So that's a really cool function of it. And it all works natively in the cloud, and in many cases, you're actually using SDN when you have your VPCs running in AWS, and you may or may not know it. Any other questions before I move out of the demo here?
I have a question.
Yes, sir.
Looks like at the top there, you have something going on with the API. Looks like it's JSON format.
Yes.
Is that the API RESTful?
So yes, I wasn't intending on showing everyone this, but I'll roll with it here. So there are two ways of interacting with the SDN controller. One is you can just send curl commands. So this is some test flows that I set. This is my oh shit flow that deletes all of these SDN controller, so I can stand it back up if something breaks during the talk. Or what I've done is you can interact with them through Python. So this is some code I wrote that actually interacts and sends flows to the switches that I will be demonstrating a little bit later. So yes, it's a RESTful API. You can pull whatever information you want on the network and push whatever updates you want to your SDN controller from there. Somebody over here? Yes, sir. I'm sorry? I will not be talking about a ton of security vulnerabilities in OpenFlow. No. There are ways to attack OpenFlow, and there are problems with it. For one thing that myself and my partner discovered was the packets from in the OpenFlow protocol are very predictable. And so you can begin to discern what packets and what kind of network it's on if you have access to control channel traffic. There's no padding inside the packets. They have a fixed size. So you can begin to identify what packets are going across and identify the scope of the network, potentially even start building rainbow tables if you start cracking some of those packets. So those are a couple of problems. There's no randomness inside the packets is one of the issues with it. But this one, it's a little more leaning blue team this side, and talking about how we can defend our network and how SDN can help us in many ways. So I will move on now. Close this out. Oops. So, why do we care about this? What have we learned so far? Who cares about SDN? Well, so one of the cool things is we now have absolute control over every aspect of traffic, layer 1 through layer 7. So we can view every bit of traffic, monitor it, react to it in any way possible, because we now have complete insight into everything depending on how much you want. You can apply traffic policies, as we discussed, to users and groups of users and floors in your building. That all can be applied, and they can only be allowed access to what they need access to. Once again, flow tables can be created within flow tables to create dynamic decisions of what we want, how we want traffic to behave at really every layer of the OSI model. So those are some cool things about the level of control and monitoring that we have. That's really been a game changer within SDN. So a couple of the use cases for security and why this matters there is what are users actually doing? Why do our users, and not even our users, but our servers, our cloud systems, who are they actually talking to? And why do they need to be sending traffic that way? One great example of a policy is, say your company has put out a policy that we only allow our servers to talk to internal DNS. I'm sure that's a policy at many of your companies. How many of your companies, though, is that really working and applied globally? Or if you go into your Splunk or whatever your SIM is and do a search on 53 and see how many other DNS servers are calling out to. With SDN, you can identify a DNS packet no matter what the server is and rewrite it to call to your DNS server within the traffic policy itself. And so you no longer have to really, obviously you want your stuff configured properly, but at this point you can overwrite it and fill in your own information and ensure that all traffic queries your own DNS server. As you can rewrite the content of the packet, you can rewrite the source and destination IP and MAC addresses. You can totally spoof your own systems so that they only call to what you want them to. How do you limit access to vendors and third-party folks that need to connect to your network? You have some machinery that needs a vendor connected to do troubleshooting and debugging. How do you ensure they're only doing what they're supposed to? VLAN segmentation is okay at best. Firewalling them off, it requires changes in firewall rules and lots of manual input to try to meet each vendor's needs. This can do it dynamically in many ways. And then how do you handle BYOD, Internet of Things devices in your network? How do you ensure they're properly sandboxed off and only having the access they need? So these are all security use cases where SDN can come in very handy and can fill a lot of those gaps. Time check here. Okay. So let's go into a little more of the security side of things here. With the dynamic control we have over some of these things, what does that provide us on a security side? Well, in many cases, we can do location-based access control now from an SDN because you know where all your switches are, you know what users are connecting to them, and you can use that in conjunction with many other factors to actually have provision network resources based on a user's location, even within your building. So with what I'm going to show in a minute here, with a big data security type model, kind of moving away from the SIM and moving into a big data model, the data lake that you collect can have badging data, it can have video feeds, it can have any amount of security data about your network, and the SDN controller can actually look through that and pinpoint a user's location and pinpoint the access that they're allowed to have. So it can say, hey, this user just badged into San Francisco. Why did he log into Dallas? And why did we not see him on the security footage in San Francisco? And it can put all that together and pinpoint where a user is in many cases, or grant them access. So the legal team is allowed certain access to certain resources that HR, for example, is not allowed to. That can be easily provisioned just from an infrastructure side, long before your access control and your file sharing and whatever other security measures you have in place. I'm talking at an infrastructure level, you can control access to those sorts of things. Once again, security tool Mageddon is what I like to call it. You go over to Black Hat, you go over to any of those places, and you see infinity of security tools. And in many cases, this vendor agnostic type of deployment can answer the call of some of the security tools and reduce the number of security tools you need. As we said, using patterns within your network and machine learning, you can start looking at bandwidth consumption and application usage, account behaviors, and actually provision network or limit network resources based on those. How many of you have heard of Apache Spot? Not a whole lot. It's a fairly new project. It was started as an Intel project that they wanted to use to. Okay, thank you. That Intel wanted to use to demonstrate to handle the massive amount of data that they're handling on a daily basis. And so Apache Spot was kind of their answer to solving some of these problems. And they've since moved it into the open source, and it's about 2 years old, and has recently become an Apache incubating project. I'm not involved in the Apache Spot project. I just thoroughly enjoy it, and quite honestly, much of this next portion could not have been done without a lot of help from the dev team there. They were phenomenal working with me, the team there from Intel, on getting this done. So, what is Apache Spot? This is the kind of verbiage from their site. It's a community-driven project providing advanced analytics and comprehensive visibility across all security data using an open, scalable platform. It is based on Hadoop, and they're currently working on multiple different ways of ingesting multiple different types of data. So, initially, the Spot ingests various network telemetry, such as NetFlow or SFlow data, PCAP files, DNS information, proxy information, and ultimately we'll be able to ingest user information, logins, user behavior, all that sort of thing can just be ingested into their data lake. And that's where it goes into their ingest framework. They're working on soon to deploy Spark streaming to allow larger quantities of data than they currently do, but it's all built on Python, very easy to understand, very easy to code to. They then apply their machine learning model to it to determine patterns in the network data and find outliers. And from there, their operational analytics portion actually evaluates that and presents that to the analyst. So let's check it out here. So this is kind of the network architecture I'm going to use for this particular demo. Right now, let me zoom in on it. So right now, there's the kind of top of the rack switch on each of the racks. There is 2 attacker hosts, as you can see, host 1 and host 2 there, and then we have a honeynet here, which is our spoof network that we're going to make attackers think they're in our real network, but they're actually not. So that is designated by Winnie the Pooh. Oops, I need to go over here. Make sure all my stuff cleared out. Perfect. So let me walk you through the Spot tool real quick here. So this is Apache Spot. This is what the dashboard looks like here, and as you can see, there are any number of data entries here. These are the orange ones or yellow ones are signifying public IP addresses, and the blue ones are signifying internal IP addresses. This was just some sample data that we generated for the purpose of this talk. Any one of these can be investigated, and so you can pull up any one of these flows, for example, and it will show you all the hosts communicating to that system, and of what types of communication and what sorts are. Over here, there's the suspicious flows. This identifies traffic that is anomalous in some way, and identifies things that should be of concern. Now let me refresh this real quick. So for example here, this is a suspicious flow. Our 10.0.0.1 was identified as a suspicious attacker, and so you can see various types of enumeration attacks going on down here in the window, and you can score each of the types of attacks based on your environment. And so 10.0.1 was here, sending all sorts of weird things to our victim at 10.0.128.103. Now, where that comes in with SDN is the integration with that sort of architecture and the SDN infrastructure. And so what this allows is for that attacker to be identified and then action to be taken. Now, I'm doing it manually here, but in many cases, you could very easily do this dynamically. There's certain behavior that you never, ever want to see on your network, and you can immediately do any number of things, send flows to the switches based on that. So let me stand up my mininet here. I am running very low on time here, so we're going to blast through this. What we're showing here is we can now send, where are we, Apache Spot? We can now send flows to the switches. So I'll just skip to the juicy one here. Say there's this suspicious IP address, is this 10.001 here. I want to investigate it. And I want this particular IP, I don't want to block his access, because as soon as his access is blocked, he games up, the attacker knows that we're in. So what I can do is submit flows to the SDN and actually honeypot that host and rewrite all of his traffic, so he thinks that he is in a different network. Let me pull this up here. Got to rush through this here. So as you can see here, you remember the topology that I showed previously. Basically, what this has done here is it's injected flows that have made the topology connect here. It's not physically connected, but to the attacker's point of view, they're actually talking. So any traffic that he sends that is triggered by him speaking to another host, he's immediately transparently redirected here. So his traffic, as soon as it hits this switch, is rewritten with a new IP address, new subnet, and these switches all know how to handle that malicious subnet. So they're added to a malicious type of subnet. These switches know how to handle it and immediately redirect it to our honeynet, which is down here. And that honeynet now can handle, you can stand up VMs, you can dynamically actually stand up whatever you want around that attacker and make him think he's actually in your network, and in reality he's not. He's just being very closely watched. And so this is all done though at an infrastructure level. This is not, this doesn't require agents on computers, this doesn't require anything other than the SDN infrastructure. And so detecting those types of attacks, there are various plugins. Intel is currently working on the Open Security Controller, different things that can plug into this that can give this machine learning model this kind of dynamic knowledge to redirect traffic on an infrastructure level. And so when I said Skynet can now fight back, that's exactly what this means. This is the network infrastructure actually taking charge of itself. This isn't a software application running. This isn't anything else. This is actually the infrastructure protecting itself. Now, before I get Oscared off the stage here, finally a helpful SDN tool. Now, I don't mean there's no other helpful SDN tools. I just mean finally, this is my last slide. This takes S-flow information from the network and writes it to a mininet topology, and then communicates those flows to the controller. So basically, you can translate any network into an SDN. Even a lab network, even whatever you want at home, that you want to test this out. I was trying to find out good ways to migrate to SDN, and there's not any good open source ways of migrating from a traditional network to an SDN. And so that's where this is supposed to come in handy. This will actually take your regular S-flow, NetFlow information you're sending from your switches, point it at this little application, and it will start building mininet topologies based on that and sending those flows to a controller. And those flows, by the way, don't have to be sent to a mininet. They can definitely be pointed at a regular controller, and you can actually migrate. Please don't do this in production and then call me and like. In theory, you can migrate a production network with this tool. I wouldn't recommend it, but check it out. My issue was I was trying to think of a creative name for it. So it takes S-flow information, writes it to a mininet topology, FlowRida. It just made sense. So anyway, that's all I've got, folks. Are there any questions before I get booed off the stage here? Any questions? Wonderful. Well, thank you so much. I appreciate it. I'll be around here afterwards. I'd love to talk. Thank you.